Hackers don't really bother trying to break down your front door anymore. In 2026, they just poison the wood you used to build it.
Exactly.
Welcome to the Deep Dive. Today, we are unpacking the 2026 threat landscape, and we're specifically zeroing in on what the cybersecurity world has basically dubbed the silent killer.
Right. AO3 2025.
Yeah, software and data integrity failures. So our mission today is to extract the most critical insights from our sources and tear down that hidden infrastructure that you, me, and literally every enterprise on the planet implicitly trusts.
Yeah, we're talking automated deployment pipelines, third-party libraries, the underlying logic of the apps you use every single day.
Okay, let's unpack this. To really grasp why this specific threat category is just so devastating, we have to completely reframe how we think about vulnerabilities. We aren't talking about, buffer overflows or SQL injections anymore.
No, not at all.
This is the complete weaponization of the software supply chain.
It really is. It is the ultimate exploit of trust. I mean, when we analyze the architecture of modern applications, the core vulnerability isn't necessarily a flaw in the code you wrote yourself.
Right.
These integrity failures happen because an application relies on code or data from a third party without mathematically verifying its source or its authenticity.
We just sort of blindly trust it.
Exactly. We are so accustomed to the speed of modern deployment that we just accept the digital systems around us as legitimate. We assume the updates we install and the libraries we import are safe, simply because they come from a recognized pipeline.
But the moment you interrogate that chain of trust, you realize how fragile it actually is.
Very fragile.
So, if blind trust is the core vulnerability here, the most logical place to start is right on the factory floor.
The CI/CD pipeline.
Yes, the CI/CD pipeline. So modern applications are assembled. They're not really written from scratch, right? They use these highly automated continuous integration and continuous deployment pipelines. It's basically a digital assembly line.
That's a great way to put it.
And we all know the benefits of CI/CD, but the data points out that attackers have completely shifted their focus here. They aren't trying to breach the production web server anymore.
Why would they? They go for the build agents.
Right. The developer workstations, the runners on platforms like GitHub Actions or Jenkins. Through misconfigured repositories or, leaked credentials, they inject malicious code directly into the golden image.
Right, before the software is even compiled.
Yeah.
And the tactical advantage for an attacker here is just immense.
Oh, I'm sure.
I mean, think about it. If you compromise a production server, you get one server. But if you compromise the CI/CD pipeline, you get every single user who downloads the next official software update.
Wait, I have a question about that.
Sure.
If the official update itself is infected at the factory, like before it even ships, how is the end user supposed to protect themselves? It sounds like we're punishing the victim for trusting a legitimate source.
Well, the harsh reality is they can't protect themselves.
Wow.
Yeah, the end user is effectively helpless in that scenario.
Yeah.
They verify the signature mathematically checks out, but the system that applied the signature was completely compromised.
So that's exactly why it's a silent killer.
Exactly. The burden of verification falls entirely on the builders to secure the pipeline. You cannot expect the user to spot a poisoned update if it's literally signed by the company's legitimate keys.
Okay, so that shifts the burden entirely. So moving from attacks on the internal assembly line, let's explore how builders are tricked into bringing poisoned external parts into the factory.
Right, because modern apps pull in thousands of external dependencies.
Thousands of them, yeah. They use public repositories like NPM or PyPI. This brings us to dependency confusion, which is just a wild concept.
It really is. It exploits the very package managers that developers rely on to save time.
Right, so let's say an app pulls thousands of these small libraries. An attacker discovers the name of a company's private internal library.
Right, something proprietary.
Yeah. And then they upload a poisoned version of that exact same library name to a public repository, but they give it a way higher version number.
Like version 99.0.0.
Exactly.
Yeah.
It's like ordering a specific brand of flour for your bakery from your own private supplier, but someone slips a poisoned bag with the exact same name onto the delivery truck just because it has a shiny new sticker that says new and improved.
That's actually a perfect analogy. The build system sees that public version, assumes it's a newer update because of the version number, and just pulls the attacker's code instead of the private stash.
But wait, why wouldn't the system just default to its own private stash? Like, why is it even looking at the public internet at all if it knows it has an internal repository?
Well, what's fascinating here is that package managers were historically built for collaboration, right?
Yeah.
Not for high-security enterprise code.
Oh, I see.
Yeah, unless you explicitly configure the namespace scopes to tell the system, hey, only look internally for this specific package.
It just queries both.
Exactly. It queries both. And its underlying logic is designed to prioritize the highest version number to make sure you have the latest security patches. It just assumes higher number equals better.
It's just a complete failure to verify authenticity. It trusts a self-reported version number over actual cryptographic routing.
Right, which is a perfect transition into how systems blindly trust data structures in general.
Oh yeah, insecure deserialization. Let's dig into that.
Yeah, so insecure deserialization is essentially a logic exploit. We aren't talking about standard JSON payloads here. We're talking about serialized objects.
Right, because JSONs is just raw data like strings and integers.
Exactly. But serialization preserves the actual state and logic of a complex object. Like if you're in Java or Python and you want to send a complex object across a network, you serialize it into a byte stream.
You freeze it.
You freeze it, and when the receiving server deserializes it, it reconstructs the exact object, complete with its internal methods.
Okay, but if the server reconstructs it without checking its integrity, it basically accepts a booby-trapped object.
Right. Because the server automatically invokes certain built-in methods to wake the object up. Attackers manipulate the serialized data to chain legitimate classes together into what we call a gadget chain.
And that leads to remote code execution, right?
Exactly, RCE. The server unpacks the payload, follows the attacker's gadget chain, and inadvertently hands over full control of the server.
Wow. Okay, so now that we understand the mechanics of how trust is exploited on a granular level, let's examine what happens when information integrity completely collapses in the real world.
Yeah, the blueprint breach.
Right. There is this massive real-world case study from our sources involving an organization's internal Bitbucket repository. It was left completely exposed due to a security misconfiguration.
A single misconfiguration.
Yeah. Hackers found the unprotected link, and they cloned 150 gigabytes of proprietary source code. The platform just failed to verify the identity of the requester before handing over the entire blueprint of their infrastructure.
Which is catastrophic.
Yeah, but here's where it gets really interesting. They didn't steal the code to copy the app.
No, they never do.
Right, they stole it to find the keys to the kingdom. Inside the code, the attackers found hard-coded API keys and database credentials.
Which allow them to pivot straight into the production environments.
Exactly, and execute massive account takeovers. But I have to push back here. We have tools for this now. Is leaving API keys in the source code just sheer laziness on the developer's part? Or is there an actual structural reason this keeps happening?
It is definitely a structural issue. You have to contextualize the downstream effect here. In complex modern deployments, convenience almost always overrides security.
Speed over safety.
Exactly. Setting up proper identity roles and managing secret rotation takes a lot of engineering overhead. So when a developer is troubleshooting a service that keeps failing, the fastest way to test it is to just temporarily hardcode the API key.
Just to see if it works.
Right, and they always intend to remove it before pushing to production. But in a fast-paced CI/CD environment, pull requests are merged rapidly. The secret gets committed.
And even if they delete it later, it's permanently in the Git history.
Exactly. Which leads to catastrophic information integrity failures.
Okay, so having seen how attackers exploit trust in code and data, let's shift to the offensive perspective. How do attackers exploit trust in identities?
This is where we need to look at insights from cybersecurity.
Right, the methodology framework.
Yeah, the offensive goal at cybersecurity is always to look for the unsigned and the unverified.
So what does that look like in practice?
The most prevalent example is token replay.
Okay, with JSON web tokens or JWTs.
Exactly. If a server issues a JWT but fails to verify its integrity against the specific session that requested it, attackers can literally replay that token to hijack an account.
It's like taking someone else's VIP wristband at a concert.
Yes.
So what does this all mean? Like, if the server is the one issuing the VIP wristband in the first place, why doesn't it bother to check if it matches the actual person wearing it?
Because there is a massive disconnect between issuing a credential and verifying the context of its use. The server checks the cryptographic signature on the token, right? It says, yes, I issued this. But it fails to check the client fingerprint, like the TLS session ID.
Oh, so the token is real, but the person holding it is wrong.
Right. Another huge issue here is predictable UUEAs.
Identity integrity failures.
Yes. This happens when an app issues identifiers based solely on public data, like a mobile number, without a verified handshake.
Wait, how did they bypass the handshake?
Through parameter manipulation. Say there is an API endpoint to validate a one-time password, an OTP. The attacker intercepts the request and swaps the mobile number in the JSON payload to the victim's number.
Oh, wow. So they trick the server into trusting their identity because the server fails to verify the integrity of the binding between the OTP and the actual session.
Exactly. The core CySec frame rule is compromise the process and you compromise the product. The server just blindly trusted the mobile number provided by the client.
Okay, so we've thoroughly dismantled the infrastructure of trust here. It's pretty bleak.
It's a mess, yeah.
But to close the loop, we must reconstruct it using what the sources call the zero trust chain. So let's talk remediation. What is the cure?
The first step is absolute code signing.
Right.
Every single software update, every internal library, every container image must be cryptographically signed. If that signature is missing or wrong at any point in the pipeline, the system just blocks it.
Mathematical proof over implicit trust.
Exactly.
The second component is the SBOM, the software bill of materials, which is basically maintaining a live inventory of every third-party component you use.
Yeah, it is critical.
It's like an ingredient list in a restaurant kitchen, right? Like if there's a sudden E. coli breakout in the spinach, you need to know exactly which salads have spinach right this second so you can pull them.
That's exactly it. If a library like log4j becomes poisoned, you must be able to find it and kill it instantly across your entire architecture.
Because if you don't have an SBOM, you spend weeks just trying to find out if you're even vulnerable.
Right. If we connect this to the bigger picture, visibility is just as critical as prevention in a zero-trust architecture. You also have to harden the repository itself.
No more hard-coded credentials.
Never. You use a secure vault for your secrets, and you enforce multi-factor authentication on every single developer's Bitbucket or GitHub account.
And finally, to fix those identity exploits, you have to verify at the server.
Never trust a client to tell you who it is.
Right. Identity parameters like mobile numbers have to be retrieved exclusively from a secure server-side session, not from some client-side JSON payload that anyone can tamper with.
Precisely. The server must be the single source of truth.
Well, this has been quite the journey. To summarize, we've gone from how attackers bypass the front door by poisoning CI/CD pipelines all the way to the absolute necessity of the zero trust chain. Because defending the front door is completely useless if the house itself is built with poisoned wood.
It really is.
So that covers ASO 3 2025. In our next deep dive, we'll be tackling CySec Frame Day 4, which is cryptographic failures. We're going to get into the actual math that keeps or loses your deepest secrets.
I'm looking forward to it. But I do want to leave you, the listener, with a final thought to mull over regarding supply chains.
I'm sorry.
If the entire solution to supply chain attacks is demanding cryptographic signatures for every update in every library, what happens when the very system responsible for verifying those signatures gets compromised?
Oh, wow.
Yeah. Who signs off on the signers?
That is a terrifying thought to end on, but a very necessary one. Thank you for walking us through this. We will catch you next time on The Deep Dive.